Okay, we're going to continue on lecturing. I think we're in the middle of acid and bases officially, so we'll hopefully knock that out. Then we will shortly be moving on to organic, I think, this week. All right, so last time we talked about acids and bases before the exam, I believe. And remember that we have kind of the Bronsted-Lowry definition of an acid or a base. And a Bronsted-Lowry acid is a proton donor, and a base is a proton acceptor. And sort of the consequence of that sort of relationship is it creates sort of pairs on opposite sides of the arrow. So when we have an acid and a base, they create what are referred to as the conjugate acid and the conjugate base. And basically, the acid on one side is related to the conjugate base on the other side, while the conjugate acid is related to the base on the other side. And the difference, as we talked about, should only be one H plus difference. Again, the acid here is going to send that H plus over to the base. So the conjugate base will have one less, there we go, H plus than the acid started with. And the base will accept the H plus, which means the conjugate acid there will have one more H plus. Remember that they do have to sort of be only a difference of one H plus in order for them to be partners and pairs. They cannot be anything more than that. Otherwise, they are not related to each other. Always the regular old acid and bases are found on the left-hand side of the arrow. All your conjugate acid and bases are on the right-hand side of the arrow when you look at. We then talked about sort of the idea of water, and water actually could set up what is referred to as an equilibrium sort of reaction and basically make H plus and OH minus in solution, because water, as we talked about, is amphoteric, which means it could act both as an acid and a base. So in certain cases, the water will give away an H in plus, and the other water will accept the H plus. This sets up an equilibrium, which means we could write what is referred to as an equilibrium constant for water, which is oftentimes referred to as Kw. And Kw is the concentration of H plus times concentration of OH minus. And for the most part, that equals 1 times 10 to the minus 14. The other really important thing, as we talked about, is H plus and H3O plus are essentially the same thing. They could be used interchangeably, both in sort of equations and reactions. So another way that you would see Kw written is the concentration of H3O plus times concentration of OH minus. So pretty much wherever there's an H plus, you could swap in there the H3O plus. Once again, as well, the brackets do mean concentration. And usually that is molarity that we're talking about when we kind of use those brackets there. This allows you to determine whether or not a solution is going to be acidic, basic, or neutral if you know really the H plus concentration, which is kind of the acid part of the solution, or if you know the concentration of the OH minus, which is really like the base part of the solution. And you can find either one by basically taking 1 times 10 to the minus 14 divided by the other one that you were given. So it's really the exact same calculation, regardless of which one you're given. Also really important, as we've talked about, I think last time as well, you definitely want to make sure that you are using your exponent button in this chapter for sure. Otherwise, you will find yourself I will say way off, but you'll find yourself with your answers looking off, or they'll look like almost right, but not really right. What we can do with these numbers here is compare them. So if the H plus concentration is larger than the OH minus concentration, that pretty much means that the acid part of the solution is bigger than the base part of the solution. It would be an acidic solution. If the H plus concentration equals the OH minus concentration, then they both actually have a concentration of 1 times 10 to the minus 7, which means it is going to be neutral. And if the H plus concentration is less than the OH minus, or really the base part of the solution is larger, it would be a basic solution. The relationship between H plus and H3O plus is basically opposites of each other. So as one increases, the other decreases. So they kind of work opposite in the solution. So really, as the concentration of H plus increases, the concentration of OH minus will decrease, and again, vice versa on that. H plus goes down, OH minus goes up. Any questions on any of that? I think we talked about last time. Seems vaguely familiar. Hopefully that was his class. I hope. Any questions? All right, so if I'm not mistaken, I think we did that first example using KW at the end there. So I think we're on to the next example. So let's take a look at that one. And let's see what that one looks like here. So I think we're on, say, this example here. So we'll just forget this and let's just calculate the concentration of OH minus, and is it acidic, basic, or neutral? So take a moment, make sure your calculator still works, and calculate the hydroxide concentration and see if it's acidic, basic, or neutral in this case. Okay, let's take a look. So once again, here we will use KW, which is our H plus, and our OH minus concentration equals 1 times 10 to the minus 14. In this case, we're given the H plus, so we want to calculate the OH minus. So our OH minus concentration will equal 1 times 10 to the minus 14 divided by what was given, 2.8 times 10 to the minus 5. Once again, we want to make sure we use our exponent. So that's going to be a 1 exponent button negative 14 divided by 2.8 exponent button negative 5. Going to get us a 3.6 times 10 to the minus 10 in this case. This does use molarity as it is a concentration. First off, any question on that calculation? Now we want to compare our H plus concentration to our OH minus concentration. And looking at it, it is actually the H plus concentration that's larger, as 10 to the minus 5 is a larger number than 10 to the minus 10. So in this case, the H plus would be larger than the OH minus, and that would tell us that this should be acidic. Any questions on that? Again, the negative is really important here. As we talked about, I think last time, -5 means you're going 5 places that way and putting zeros. -10 here means you're going 10 places that way and putting zeros, which makes it a much smaller number. So again, negative exponent, smaller number, smaller negative exponent is the larger number overall. Any questions on that one? And let's take a look at this one here. We'll do one more. We'll just do the same thing. Let's just calculate the OH minus, and again, acidic, basic, or neutral. Okay, so once again, here it's going to be our KW. And again, it really doesn't matter which one they give you. It is pretty much the same calculation always. So in this case, we are looking for the OH minus. So we're going to take our 1 times 10 to the minus 14 and divide it there by 1 times 10 to the minus 9. And again, making sure you use your exponent button there gets us 1 times 10 to the minus 5 in this case. And in this situation, it is actually going to be the basic part here that is larger than the acidic part. So the OH minus is going to be greater than the H plus, and that would tell us that it is basic in this case. Any questions on KW? Again, I would say most people mess up by not using their exponent button. Yeah, so make sure that you put it in correctly along the way. And again, once again, this can also be H3O plus. Again, it's the same thing. All right, so let's then talk about really a more convenient way and probably a common way that we talk about things being acidic or basic, and that is the pH scale. So the pH scale is a way that we use to represent really how acidic the solution is. It's not negative here, that's just from PowerPoint. But to calculate the pH here, the pH is equal to minus the log of the H plus concentration. Once again, this is another one where you can use H3O plus if you like. Again, they mean basically the same thing. That is a measure of how much H plus is in the solution. The pH scale runs from 0 to 7 to 14, and below 7 is acidic. Above 7 there is basic, and really dead on 7 there is neutral. 7 sort of your center point. As you go below 7, you become more acidic. As you go above 7, you become more basic. And you should always use the pH probably to determine whether or not a solution is acidic, basic, or neutral, because that is usually the scale most people have in their head. Now, in terms of this equation and the rest of the one we're going to talk about, if you have a display calculator, you should punch it in exactly the way it's written. That, again, is the negative number, not the subtract button. So that's the negative and the log button, and your concentration using your exponent button. If you have a non-display calculator, this equation and the rest of them, you got to go backwards. So you got to start with the number. You got to hit log and then hit the negative. If you're not sure what type of calculator you have, hit log. If it says error, congratulations, you have a non-display calculator. If it says log, congratulations, you have a display calculator. So that's the way you can quickly determine which type of calculator you have. So if you have a display calculator, you pretty much punch it in the way it's written, the formula. Non-display, pretty much you got to work your way backwards if you have that type of calculator. So to calculate this, we would put in obviously our H plus concentration, making sure that we do use, again, our exponent button when we do that. Let's talk about significant figures and pH. So when you calculate something like pH, the number of decimal places in your pH value or pH-like value should equal the number of significant figures in the concentration, and vice versa. So however many sig figs there are is how many decimal places you should have. So let's give this one a go here. What is the pH of the right number? Again, if you have a display calculator, you should be punching it in this way: the negative button, the log button, 1, your exponent button, negative button, and 5, and like an equals button would be good. If you have a non-display calculator, you should be rolling backwards, which means you'd be punching in 1, exponent button, negative button, 5, then the log button, and then the negative button, and then you might have to equals at the end of that. So whichever way you do that, you should end up with the number 5, I hope. Yes. Any questions first off on that? So yes, so it actually tells you in the name of it what you need to calculate. So pH means pretty much you need the H plus concentration. Yeah. So you got pH, that's definitely what you need. Yeah. Usually in a non-display, when you hit this, when you take basically the log of that number, it'll make it negative. So that's why you have to usually hit the negative to turn it into a positive. Why don't you got a positive number when it's all done? Yeah, it might be. I don't know. I didn't make all the calculations in the world. But in most cases, though, when you hit log of the number, it usually will be negative number. So that's turn on. Just want to make sure the pH is positive, no matter how you do it at the end. All right, let's talk about how we should report this answer. That's going to be a 5. We want to report 5.0, 5.00, 5.0000. That feels like a lot of zeros, so I'm just going to get rid of that one. Which way should we report this? This should end up being a pH of sig fig wise. Should be this one. So it should be this one, and basically what the rule is, this number here, which is the concentration, has 2 significant figures, right? And that means I end up with not sig figs, but decimal places. So it is sig figs to decimal places when you're going to the pH value. And by the way, opposite. We'll talk about going opposite, obviously, as well. So if you're starting with the pH, you got 2 decimal places, your concentration should have 2 significant figures. So sig figs, 2 decimal places. Question on that? Acidic, basic, or neutral, this one? This one is acidic. Yes, it is less than 7. So this guy would be acidic. Any questions on any of that there? Okay. All right, so why don't you try both of these here? Calculate pH of each, and while we're at it, is it acidic, basic, or neutral, each of them? Look, so we'll start the first one here. We have the H plus, so we can go into our pH is equal to minus the log of the H plus. That gives us minus the log 2.1 times 10 to the minus 5. You want to put that into your calculator, whichever way works, I guess. So minus the log of 2.1 to the minus 5. Going to give us a pH here of 4.68 in this case. Once again, that is 2 significant figures. Gives us 2 decimal places as we go that way. That is less than 7, which means it should be acidic. All right. Once again, when you're asked that question, by the way, there is just one answer. Cannot be acidic, basic, and neutral all at the same time. So it's got to be one of those. I would say I've never had anybody give all 3. I have people give 2, like it's acidic, but and it's also basic at the same time, which I guess would mean that maybe it's neutral. I don't know. But it should only be one answer when you do that. All right. Number 2 here. We cannot go directly into our pH equation here, as that is the OH minus concentration. So we can use our KW, if you like we did before, to actually calculate the H plus concentration. 5.9 times 10 to the minus 8. And if we do that, that's 1 to the minus 14 divided by 5.9 to the minus 8. Going to give us something like 1.7 times 10 to the minus, not 8, 7 maybe. 1, 2, 3, molar. Now we could go into our pH equals minus the log 1.7 times 10 to the minus 7 in this case. Gets us basically a 6.77 as our pH. And that would be technically slightly acidic here. Bless you. We're going to go with, just so there's no confusion, we're going to go with 7 on the nose is neutral. So there's no misunderstanding. We don't have to figure out where neutral sort of wiggles. The real answer is 7 on the nose actually is neutral. So this is a little bit below 7. So we'll go slightly acidic, a little bit above 7. We'll go slightly basic as well. Now, if you just blindly went into that equation there and did minus the log of 5.9 times 10 to the minus 8, and you got say this number here, you would have got like 7.23. All is not necessarily lost, other than the fact that that is not the pH, because this is the OH minus concentration. All you did was sort of jumped ahead a few slides. This is the OH minus concentration, which means if you use the OH minus concentration, you calculate what is known as the POH, not the pH, which is a different scale. It runs opposite actually of the pH scale. Why that might be helpful is there's a nice relationship that if you take the pH plus the POH, it equals 14. Which means you could get to the pH by taking 14 minus 7.23, and you'll end up back up here. So if you did that, first off, though, is not, again, the pH, it is the POH. And like an earlier question, POH tells you need the OH minus concentration to calculate it. And you can subtract 14 and get to the pH as well. So there is a couple different ways, obviously, that you could get to the end result there. Any questions on that? All right. What we just did. All right. So the pH scale is based on the log of 10, and basically for every pH change of 1, it's a power of 10 change that occurs. So if you have a pH of 3, it's 1 times 10 to the minus 3. pH of 4, 1 times 10 to the minus 4. pH equals 1 times 10 to the minus 5 for the H plus. Once again, this is just PowerPoint, so none of these are negative. As the H plus concentration increases, that means there's more H plus in the solution. The pH actually goes down, and vice versa. As the H plus concentration gets smaller, the pH will go up. And that is really because of the relationship we talked about earlier. Basically, if the H plus concentration goes up, there's less base in that solution, and we see the result of that pH goes down. And vice versa, if the H plus goes down, that means we have a lot more of the OH minus or base part of the solution there. And the result of that is we will see the pH go up in that case. So again, they do run opposites of each other, the H plus OH minus. And depending on how much of one versus the other you have in that solution, again, will tell you if it's going to be maybe acidic or basic. So there are several ways we could measure pH. We could use a pH meter like so, which is a nice one. It measures basically the H plus concentration in the solution, gives you a nice digital display. You usually calibrate it with solutions that are like pH 4, pH 7, and pH 10. And basically the way it really works is its voltage. So you put it into a pH of 4 and go, this is like the voltage for a pH of 4, and then this is for the voltage of a pH of 10. And they do like a little calibration curve and determine it. Onto your pH paper, it changes color. You then try to match up the color scheme there on the little scale, and it gives you an idea. Obviously not as probably precise or accurate there as our pH meter, but gives you an idea. We also talked about litmus paper. It doesn't really give you the pH, but it will tell you if it's acidic or basic. And typically litmus paper again turns red. And if litmus paper turns blue, it is basic. And once again, it really doesn't necessarily give you a pH value, but it'll give you an idea if your solution acidic or basic. So here's our pH scale, and we got our bases here. So oxide up. We got some strong acid there on the bottom. We got pure water there at 7. If you take regular water or water has been sitting out a while, it will be pH of 7 or maybe a little less, probably in that range. As it picks up some carbon dioxide from the air, creates carbonic acid, increases the H plus concentration in the water, lowers the pH and stuff like that. So sometimes people are surprised. They stick it in and go, whoa, my water is not a pH of 7. But it's really a lot of times acidic as you go through it. A lot of our acids here obviously are in the acidic range, and again, our bases there in the basic range. So we sort of jumped gun there on the last slide, but there is obviously similar scales to pH, and one measures the POH. And again, the POH scale does run opposite. So the pH scale is 0 to 7 to 14. And once again, that's acidic there. Below 7, that's basic. On the POH scale, it is opposite, which means between low 7, it's actually basic. Above 7 is acidic. They're basically opposites of each other. So if you have a low pH, you have a high POH, and vice versa. This is the situation where people give that answer of it's acidic and basic because they calculate the pH and go less than 7 is acidic, and then they calculate the POH and go it's above 7 is basic. So again, only one answer for that. I highly recommend that you look at the pH value, as that's usually the scale everybody has in their head, and again, just give one answer for that. So there is a variety of ways we could solve some of these problems based on sort of our method here. We could use obviously KW if we need either the H plus or the OH minus concentration. I get this one. We could calculate the pH, which is minus the log of the H plus concentration. We could calculate the POH, which is minus the log of the OH minus concentration. And again, as we said a minute ago, that pH plus the POH equals 14, which is a nice convenient way that maybe you might not even need to use KW in certain situations to calculate that. So a couple of things we could add to our list there of sort of acids and bases and stuff calculating is if log minus pH, inverse log of the minus pH. On most people's calculators, when you hit inverse log, that is usually will pop up a 10 and a caret, and then you want to go negative, not subtract, pH, or how a lot of people do scientific notation incorrectly. Yes, so this is actually the button and what you should use it for. On most people's calculators, that is like the top left button, the second button, the shift button, and then usually over your log is like a 10 to the x. So that is the combination there to get to the inverse log is shift or second and then log. You could also do the same thing for POH. If you have the POH, it will give you the OH minus concentration. And you could get it by taking the OH minus, exact same calculation, the inverse log of the minus POH. And once again, that usually will give you a 10 and a caret, and negative POH will do that for you. So those are two ways that if you have the pH or the POH, you can actually get the H plus or OH minus concentration directly from them, which would make you perhaps, again, not even need to use KW. Or if you have one of them, you can still use KW for the other. So it does give you a variety of different ways to do it. Any questions on those there? All right, let's try some here and see. Sure. Maybe. There we go. All right. Calculate the pH, the POH. Let's just do it all here. The H plus, the OH minus, and is it acidic, basic, or neutral? Obviously, if one of them's given to you, don't calculate it. All right. Take your calculator out for a test drive. In this case, since we're looking for everything, we have the H plus given to us here on the first one. We do have a variety of things we could do. We could use KW to get to OH minus if you want. Because we have the H plus, we could just go right into the pH equation, obviously pH. So that's what I'm going to do here first for this one. I'm just going to go right into the pH because I have the H plus concentration. That's going to be minus the log 3.6 times 10 to the minus 9. Looks like a better number, maybe. And if we do that, minus the log of 3.6 to the minus 9, that gives us a pH of 8.44. Once I have the pH, I could really simply get to my POH by taking the pH plus the POH equals 14. That would mean in this case, the POH should equal 14 minus the pH. And that would give us 14 minus 8.44. And that would then be a 556 in this case. Any questions so far? Now, since we are also looking for the OH minus in this case, as I mentioned before, you could use KW, but I'm going to use the other calculation we just talked about. So in this case, I'm going to look for the OH minus. So I'm going to take my POH here, and I'm going to calculate the OH minus by taking the inverse log of the minus POH or negative POH. And that would be, again, on your calculator. When you do that, a 10 and a caret usually will pop up. You hit the negative button, and then you put in there 5.56, close some parentheses perhaps. And if you do that, negative 5.56, gonna give me a value of, we'll call it 2.8 times 10, 1, 2, 3, 4, 5, 6, minus 6 molar in this case. Any questions on that there? By the way, in terms of sig figs, we are going backwards in this case. So that is 2 decimal places gives me 2 significant figures as you go backwards. So again, you want to kind of keep that no matter which way you are going. In this case, that would mean that this is acidic, basic, or neutral. This is basic. So we want to look at the pH here, and it would be, we'll circle here, we'll go basic. Any questions on any of those calculations? Yeah. On the top left, that's the concentration of OH minus. So I used that equation that we just saw on the previous page. The other option, you could have used KW like we did before. And you could have done 1 times 10 to the minus 14 divided by 3.6 times 10 to the minus 9. And you should get the same answer. So you actually have 2 options as to how to do that one. You either could do it this way, which was that new sort of calculation we saw on the previous page, or you could have used your standby as well, KW. They both should come out the same. That one doesn't matter. I'm sorry, which one? If you use KW, you're talking about? Yeah, if you use KW, you probably would still go by the sig figs over here, and which was 2. So you probably would end up with 2 as well. Yeah. Other questions? Okay, let's take a look at then the second one there and go through all of that. So on this one, we have the OH minus given to us. So once again, you could do 2 things. You could use KW to get the H plus, or like I'm going to do here, I'm going into my POH. Again, I have the OH minus given to me, so I could go directly into that, minus the log of my OH minus concentration, which is 9.2 times 10 to the minus 2 in this case. And that's giving me minus the log 9.2 to the minus 2. Going to give me a 1.04 as my POH. Once again here, now that we have the POH, we could get the pH by really subtracting 14 is probably the easiest way. So the pH in this case would be 14 minus the POH, which is 1.04. That's going to give us a 1296 here on our pH. And once again, as I mentioned earlier, you could use your KW to get to the H plus, but I'm going to do the same calculation as I did previously to get to the H plus using the pH. So the H plus would equal the inverse log of the minus pH. Question? So that is going to be 10 and a caret minus 12.96. And if we do that there, negative 12.96 looks like. Will get us something like 1.1 times 10 to the minus 13 molar, which again, if you use KW, should be pretty much what you get there. Maybe slightly different if you have a little bit of rounding, but pretty much should be the same number, as there shouldn't be too much rounding sort of happening at that point. Yeah. How are you punching this in? They're asking? Yeah. So you want to let me go back a page here, maybe actually. So to do the inverse log, and again, on most people's calculator, you first want to find obviously your log button that you've used before, and usually above the log button, there's like a 10 or X or something like that. And usually what you need to hit is top left of your calculator, which is either a second button or a shift button up there. Most calculators have one of those 2. And when you hit first the shift and then the log button, what it should probably display is something like that on your calculator. And then you want to hit the negative button and then obviously the pH or the POH. Yep, you're welcome. And again, if you have a non-display calculator, you would need to put the... If you have a non-display calculator, you have to put the number in first, then make it negative, and then hit second and log, and that will do it for you if you have a non-display. Yeah. Other questions on that? Okay, so those are 2 different calculations. When you go negative log of the concentration, you get like a pH or POH number, like somewhere between 1 and 14, basically, or 0 and 14. When you go inverse log, you get like a concentration type number, like times 10 to something, negative something or something like that. Lastly here for this one, this would be basic, as the pH here is 12.96. Yes. Any questions on that there? All right, let's try a couple more here to make sure. All right, let's do this one. You got the pH of 5.67. Let's calculate everything to make sure. pOH, what is the H plus concentration? What is the OH minus concentration? And is it acidic, basic, or neutral? So try out that calculator, make sure here. Starting with the pH. Okay, let's take a look. So once again here, I got the pH given to me. So I could use the pH plus the pOH equals 14 to get the pOH, which is what the original question asked for. So that'll be 14 minus 5.67. Then we got 14 minus 5.667. There we go. That's an 8.33. At this point, I have both the pH and the pOH. And really, in this case, we have to use that other calculation. There's no value at this point. We got to at least get one of them. Then you could use KW if you wanted to. So here we will do the H plus is equal to the inverse log of the minus pH. And again, that's your shift in log button and negative pH. And again, usually it looks something like this on your calculator as you punch it in. And if you do that there, negative 5.67, looks like it's going to get us 2.1 times 10. 1, 2, 3, 4, 5, 6, minus 6, if I counted that right. Now that you do have the H plus concentration, you could, like I said, use KW, or you could do the exact same calculation with your pOH that you have here. So you could either get the OH minus by taking the inverse minus pOH, which 3. And if you do that, you will get here. You'll get something like 4.7 times 10 to the minus 9 molar. Or if you have your calculator in decimal form, you'll get a bunch of zeros with a 5 at the end because it ran out of room, basically. Yeah. So if you're not in scientific notation, you got like, probably like 8 zeros and a 5 at the end of your calculator, most likely. Again, the other way you could do it is your OH minus equals 1 times 10 to the minus 14 divided by 2.1 times 10 to the minus 6. And once again, that should pretty much give you the same number, maybe slightly different with a little bit of rounding, but it should be pretty much the same ballpark as it. In this case, we want to make sure we look at the pH here, and it is 5.76, which means it's less than 7, and it should be acidic in this case. Yeah. Any questions on any of that there? Yeah. Yeah, so in terms of sig figs, originally we were subtracting, so we would go to decimal places, which would give us 2 decimal places on our pOH. Then coming this way, using those 2 decimal places should give us 2 significant figures in the concentration as you go backwards. And same thing here, this had 2 decimal places, which should translate to 2 significant figures in the concentration. So going backwards, that's what you should end up with. Yeah. Yeah, so in terms of pH and pOH, if you're calculating either the pH or the pOH and you have the concentration given to you, however many significant figures that concentration has is how many decimal places the pH or pOH should have. And again, if you have the pH or pOH given to you and you're calculating, the H plus or the OH minus concentration, then however many decimal places those pH or POH has is how many significant figures your concentration should have. So it should be the same regardless of which way you're going. Other questions? Okay. All right, so that was fun with calculators. Just make sure you know how to punch these things in correctly. That is half the battle as you do it. Any questions on any of that there? All right. So I think we'll skip that one since we just did a bunch of those. So let's talk a little bit about pH of a strong acid. Now, although a lot of our examples have been kind of generically H plus, H3O plus, or OH minus, you could potentially be given a formula of an acid or a base. And strong acids are strong electrolytes. So something like HCl will 100% break apart into ions, H plus and Cl minus in solution. Now, there's sort of a list of like 6 strong acids. HCl is a strong acid. HBr is a strong acid. Hydriodic acid is strong. Nitric acid is a strong acid. H2SO4 and perchloric acid. All these are strong acids. So if you see one of those, you can safely assume that's a strong acid. And frankly, in our class, you could safely assume that if you're given a formula of an acid, it's a strong acid, because weak acids and weak bases is a much longer calculation that we don't talk about in this class. So pretty much if you're given a formula, it's probably safe in our class to assume that it's strong acid or strong base. But this is a list of strong acids, a list of sort of strong bases. Basically, if you go to the periodic table, you got lithium, you got some sodium, some potassium in that area. You also got some calcium. Pretty much there and down in group 1 and group 2 on the periodic table. Any of those guys with hydroxide in the formula are probably going to be strong bases, things like sodium hydroxide, potassium hydroxide, and so forth. So pretty much anybody in group 1 or group 2 on the periodic table that has hydroxide kind of going that way, kind of hang a right there to calcium and then down, will pretty much be strong bases, which means they will 100% break apart as well. So if we had a 0.1 molar solution of hydrochloric acid, in terms of calculating the pH, the most important thing here is the H plus concentration is really what we want to know. And we talked about it when we did concentration. It is a 1-to-1 relationship between the whole thing and the H plus, which means the concentration of our H plus is also 0.1 molar because it is a 1-to-1 relationship. By the way, the concentration of Cl minus in this case would also be 0.1 molar. Not that we need it for the pH, but it also is a 1-to-1 relationship. So basically we will know, and pretty much since all acids, most of these strong acids are what are referred to as being monoprotic. They have one hydrogen. Pretty much if you know the concentration of the strong acid, that will be your concentration of your H plus. So you could go right into your pH equation at that point. And that will give us minus the log here of 0.1. That will give us a pH here of 1.00, which is acidic, and as we would expect in this case. So if you have the pH of a strong acid given to you, you can simply find the H plus concentration, which in most cases will be the same as the concentration of the whole acid, and you could go into the pH equation at that point. Any questions on that there? All right, so why don't you try this one, and why don't you try to calculate the pH of 0.025 molar. We'll go with calcium hydroxide as a strong base. This is a strong base. And we'll do this guy, which is a strong acid. All right, so the first one here is a strong acid, and what that means is a strong electrolyte, which means it is not going to stay together in solution. it will 100% break apart basically into H plus and a little perchlorate action. In terms of the pH, it is the H plus concentration that's most important here. So since the whole thing is 0.025 molar, this once again is a 1-to-1 relationship. That would mean that our H plus concentration would also be 0.025 molar. And that means that's all we need to go into our pH of 0.025 and minus the log 0.025 gives us a pH of 1.60, I think. And that is acidic, which is good because that is an acid, I guess. Any questions on that one? Now, this one, though, the second one is actually a base, and it is a strong base, which means it will also 100% break apart into ions, which means we get a calcium ion and a couple of hydroxide ions here. Now, because this is a base, the thing that's important to calculate the pH is actually the OH minus concentration. That will allow you to get not the pH, but that would allow you to get the POH, and then you can subtract 14 and get to the pH. So because this is a base, we don't have the H plus concentration, but we do have that OH minus concentration. So we got to first go POH and then to the pH because of that. We do also need to make sure that we get the correct concentration here of our base. In terms of the hydroxide, it is a 1-to-2 relationship, which means we do need to multiply the concentration by 2 to get the correct concentration. And if we do that there, that would get us 0.002 times 2. Going to give us 0.05 molar is our correct hydroxide concentration. We now could go into our POH, which would be minus the log of 0.05 and minus the log of that. So that's a 1.30. Now, if for some reason you thought this was the pH, it should not make sense to you because this is a base and that is definitely an acidic pH, right? So we do need to get to the pH here, and knowing that that obviously doesn't make sense. So that's going to be 14 minus 1.3. And then if we subtract our 14, we end up with a 1270, which makes more sense because 1270 definitely is a basic pH, which is what we would expect here. Any questions on that? Bless you. So if you're given a formula of either an acid or base in our class here, like I said before, it's pretty safe. You can assume it should be a strong acid or base. You just got to make sure you get the correct H plus concentration or OH minus concentration. I will say in most cases, it's probably only going to be the base that maybe you got a situation where you got to adjust the concentration that's given to you. Probably most acids will be a 1-to-1 relationship since they're monoprotic, and that will just give you the same concentration. Any questions on how to handle strong acids or strong bases here? All right, to finish up our chapter here, we're going to talk about buffers and what a buffer is. A buffer is a solution that resists changes to pH even when you add strong acid or base to it. A very common misconception that people have about a buffer is it is a neutral solution. And it can be a neutral solution, but it could be an acidic solution. It could be a basic solution. You can make a buffer at any pH you like along the pH scale. What it means is whatever pH it starts at, let's just say we made a buffer at a pH of 4, and you add acid to it, it pretty much will stay around a pH of 4. It will go down a little bit because you added acid, but it will not have a giant jump in pH. It won't go from like a pH of 4 down to like a pH of 1. There won't be a really big jump in pH. And if you had a buffer that was at a pH of 4 and you added base to it, it would go up a little bit because you added base, but it wouldn't jump from like a pH of 4 to like a pH of 12. So a buffer is able to resist really big changes in pH, even when you add an acid or base to it. And what a buffer has to be made out of is really one of two combinations. It's either could be made out of a weak acid, and the salt is sometimes referred to, which just means it's got like a sodium or potassium there, of its conjugate base, or you can make a buffer out of a weak base and the salt of its conjugate acid. They both need to be in the solution to begin with. You cannot have a buffer that's made out of a strong acid or a strong base. So if it's a strong acid or strong base, no buffer action going to happen. The reason is because a strong acid or strong base is a strong electrolyte, as we've been talking about, when it goes for a swim. So for example, if I wanted to try and make a buffer out of HCl, when I dump HCl in here, which is a strong acid, the only thing I have in there is H plus and Cl minus. Cl minus is really only a conjugate base. There is no acid part in that solution. So this cannot be a buffer. A weak acid or a weak base, because it's a weak acid or weak base, it's one of those weak electrolytes that we talked about. And when you have a weak electrolyte, basically it stays together, but it breaks apart a little bit. So if we made, say, a buffer out of everybody's favorite example, which is acetic acid and sodium acetate. Oops, no negative there. So acetic acid is a weak acid. Sodium acetate is the salt of its conjugate base. So what happens when you actually dump like the acetic acid in to make a buffer is you will get that equilibrium set up that will allow acetic acid, and remember those two arrows we talked about with weak electrolytes, we'll have some H plus and some acetate in this solution. So what happens is in a buffer like this, we actually have a acid part and we have a base part of this buffer. And that is extremely important for how a buffer is actually able to work, is it's allowed to keep both of those things in solution. The weak acid or weak base allows both of those things to be there. You help it out by adding a little bit more sodium acetate, which kind of beefs up the acetate part of the buffer. And now you got a good amount of both of those things in the solution to begin with. By the way, here again, the real buffer components is the acetic acid in this case, and it's really just the acetate part. By the way, the relationship between these two is the same Bronsted-Lowry relationship. It's just one H plus difference. The sodium here makes it a salt of its conjugate base. Sodium is doing absolutely nothing in terms of a buffer. It's just floating around to balance out charges. It's a neutral little guy kind of floating around, but it's really the acetate part that's the base part of the buffer, and it's the acetic acid, which is the acid part of the buffer. So having both of those things in the solution is why a buffer is able to resist really big changes in pH. So to sort of demonstrate that, let's take a look at what happens when we add a strong acid or strong base to a non-buffer, like our good friend water, which is not a buffer. So if I add some hydrochloric acid to water, it is going to, as we talked about, break apart into H plus and Cl minus, which means if we look at the beaker view here, when we do that and we toss HCl into water, we basically just made a bunch of H pluses and a bunch of Cl minuses, right? In terms of the pH, we made a lot of H plus really quickly, which means the H plus concentration went up, the OH minus concentration went down, and the pH will go down a lot because you have a lot more H plus in there than you started with, right? As you basically throw the HCl in there. So we would expect, because we see H plus being made when we add it to this non-buffer, and there's a lot of free H plus, which is really what affects the pH, we would see a pretty big jump in the pH. So again, maybe your water started at a pH of 7, it might drop all the way down to like a pH of 1 by adding that to it. What would happen if we took some sodium hydroxide, which is a strong base, and added it to water? Same thing would happen. It would completely break apart into a sodium ion and a hydroxide ion. And what we would see in terms of the beaker is we would create a bunch of sodium ions, but more importantly, in terms of the pH, we would create a lot of hydroxide ions that are freely floating in that solution. And what's going to happen in this case is the concentration of hydroxide will increase, concentration of H plus will go down, and that means the pH will actually jump up because there's a lot more hydroxide or base in that solution, we will see a lot of jump in pH. It may go from pH of 7 up to like a pH of 12, a pretty big jump in the pH. Any question on that there? All right, so let's talk about what will happen if we add these exact same two things to an actual buffer. So we'll use HF and sodium fluoride, which basically is fluoride, and that is a weak acid and its conjugate base. That's really the two parts to the buffer here. So in our buffer here, we have HF, we have H plus, and we got some F minus floating around. So this is our acid part of our buffer. This is our base part of our buffer in this example. So now when I take my hydrochloric acid and I toss it in, I toss my HCl in here. When I toss my HCl, which is an acid that goes for a swim, will it react with the acid part of the buffer or the base part of the buffer? They are called acid-base reactions, yes? So when I toss my acid in there, what's going to happen is it's going to be greeted by the base part of the buffer in this case, and we're going to get a reaction between hydrochloric acid and sodium fluoride, which is the base part of the buffer, and we're going to make some sodium chloride and some HF. So what happens when we add this to the buffer is we make sodium chloride, which is basically a neutral salt. It really will not have an effect on the pH. We also will make HF, which is actually part of the buffer to begin with, right? So part of the buffer was HF, so we actually make more of the HF in this particular case. So we'll actually make some HF as a result of this. It is actually what we do not see as to why the pH doesn't go crazy. What do we not see in this reaction that we do see in this reaction when we add it to water? When we add it to water, which is not a buffer, we make a bunch of H plus. In this case, we do not make any free H pluses. So really no free H pluses are made here. And because the H plus concentration stays constant, in this case, it says relatively constant, we would expect the pH to also stay relatively constant. So because it prevents the formation of free H plus in that solution, keeping that H plus constant, it will then keep the pH relatively constant. If you actually checked it with like a pH meter, you would see the pH go down a little bit. Maybe it goes from like a 4 to like, 3.9-ish, but it again will not go from like a 4 all the way down to a pH of 1. Any questions on that? All right, well, I know we're on the end here. Let's just finish up the last little bit here. If we added our sodium hydroxide to that same buffer, which is our HF buffer and our fluoride buffer. When we add our sodium hydroxide, which is a base to this buffer, it is going to react with the acid part of the buffer. And we're going to get a reaction, which is really just an acid-base reaction that's going to occur. And we will make water, and we will make some sodium fluoride. Once again, here we made water, which is not going to mess up the pH. We actually made sodium fluoride, which is part of the buffer as well. And again, it is actually what we do not see here that we saw with the sodium hydroxide and water. When we added sodium hydroxide to water, we had a ton of OH minus being made. And in this case, when we add it to our buffer, we have no free OH minus being made, which means because the OH minus concentration will stay relatively constant, and because H plus is tied to that, the H plus concentration will also stay relatively constant. And that means that we will end up with basically the pH staying relatively constant. And that's why it's really important for a buffer to have both an acid and base part, because when you add acid to it, it reacts with the base part, prevents any H plus from being formed. When you add base to the buffer, it reacts with the acid part, prevents any OH minus being formed. So really the way a buffer works is it prevents the formation of either H plus when you add acid or OH minus when you add base. And because those aren't really going crazily being added to the solution, it's able to keep the pH. And usually what we saw here is if you had a buffer and you have an acid part and a base part to the buffer, when you add acid, you will use up some of the base, but you will regenerate the acid part of the buffer. And when you add base to a buffer, you will use up some of the acid part, but you will regenerate some of the base part. So there is what is referred to as a buffer capacity. If I wasn't paying attention, I just keep adding base. What will eventually happen is what? I will keep eating up the acid part of the buffer, right? Until there's no more. And at that point, you will blow through your buffer and you will see a big jump in pH because you're continuously adding OH minus. So basically a buffer kind of regenerates half of it or part of it as you use up the other part, and then the other part gets regenerated. And that's why a buffer can kind of resist changes in pH over a long period of time, as long as your buffer is the right molarity and, you know, to handle what you're adding to it. Any questions on buffers? All right, that wraps up chapter 10, also the last chapter of calculation.